Morning, nerds. Today we are graced with Ashley Green's art. This is a nerd emoji, apparently, but she put it on a little card, so I had to tape it. Why is it what? Why does it look tired? Well, I mean, maybe is the nerd emoji not tired looking? I don't know. I thought it looked great. Anyway, thanks, Ashley. Boop. Today we're going to talk about the last form of quadratics that we're going to graph, and that's going to be standard form. Now, a lot of things about quadratics are going to be the same regardless of what format we look at, right? Like the a value is always the same, the domain's always the same, range increasing, decreasing are always determined by the vertex. These kinds of things are always true. But I don't know if you've noticed, but each of the three forms, they all have slightly different stuff going on here at axis of symmetry and vertex. And this is no different. The equation of a parabola written in standard form is f of x or y equals ax squared plus bx plus c, where a, b, and c are real numbers. So just like we've talked about in our previous two lessons on graphing, the quadratic being up smiley or down frowny is determined by the number on the front. If the number on front is positive people smile, it points up. And if the number on front is negative people frown, it points down. So that is not new. And because we can square any number we want and multiply any number we want by some other number, our domain is going to be all real numbers. So from negative infinity out to positive infinity, nothing new there. But the axis of symmetry. This is going to be one of the very few times where, for now, I'm asking you to just memorize a formula. I'm not a big fan of just, rote memorization, strictly just know this is true without knowing why it's true. And I'm hoping that I've really imparted that onto you so far this year, is that if I tell you something is true, I'm going to tell you why it's true. For now, I just need you to trust that the axis of symmetry can be found by using x equals negative b over 2a. I will eventually show you why that's true in this chapter, but for now, I need you to just trust it and use it. All right? For now, I will get you there. X equals negative b over 2a is an x value. It's the axis of symmetry. The axis of symmetry always goes through the vertex. That means it is the x value of the vertex. So how would I get the y value of a vertex? Just plug it in. Yeah. If you know what x is, plug it in to get y. So our vertex can be found at negative b over 2a, comma. Plug that in to get the y value. I mean, you'll get a number of some sort, but just plug it in. There you go. Go ahead and throw this axis of symmetry on here, going through my vertex, because that's true for all quadratics. And that axis of symmetry is going to be the dividing line between increasing and decreasing. But before we get there, let's talk about the range. The range is a span of y values. This quadratic has a minimum, so the y value of this vertex is the bottom of my range. So we'll just say y value of vertex, comma, and it points up to positive infinity forever. Whee, like that. Bless you. Whereas this quadratic has a maximum. So the y value of the vertex is the top of its range. It's coming up from down here. It's coming up from negative infinity to whatever the y value is of the vertex. Like that, with bracket. Okay. Time for increasing, decreasing. That's the whole roller coaster thing, right? On the left side of the axis of symmetry, your roller coaster would be coming down. Whee! And on the right side of the axis of symmetry, roller coaster would be going up. So this side is the decreasing side. This side is the increasing side. So we'll increase on the right of, starting at the axis of symmetry. And forever to the right. And as we go to the right, x heads towards infinity. Decreasing on the left of, and this interval will stop at the axis of symmetry. So coming from the far left, so coming from negative infinity, heading towards the x value of the vertex, negative b over 2a. The only thing that's different when we come down to these downwards facing parabolas is my increasing, decreasing sides have switched places. Now the left-hand side is the decreasing side. So, oh goodness, a phone call. Okay, phone call over. Increasing, what we're saying, on the left side. So coming from the left, coming from negative infinity, all the way up to the axis of symmetry, x equals negative b over 2a. And reminding you that because it's a place where we change between increasing and decreasing, we're putting a bracket there. So decrease on the right side, beginning at negative b over 2a, that x value. And heading to the far right, which is where we'll find positive infinity. There is one more thing I want to mention about standard form. I didn't add it to the box, and it's because I find that when I make it a quote-unquote rule, that students try to just memorize things without understanding why they're true, and then they mix up their rules, and then they get things wrong, and I don't want that to happen. So let's just talk about it for a second. All three forms of quadratics give you something that I like to call free information, meaning something that you know to be true about the graph's coordinates without any work at all. Vertex form, from a couple days ago, just hands us the vertex of h comma k. It's free. Intercept form, which I am remiss and I don't have a copy of that with me, is called intercept form because it gives us the x-intercepts without working. We could just see them in the equation. Standard form does give us something without doing any work at all. Let me ask you, doesn't matter what kind of equation I'm talking about, doesn't matter what kind of graph we're speaking about. If I want to be able to find the y-intercept for anything, how do I do that? Daniel? Well, not even the inside. No, you mean make. When you say everything else, how are you making everything else equal 0? There we go. We're making x equal 0. Because anytime we're on the y-axis, we know x is 0. So regardless of what the equation looks like, if you want to know where its y-intercept is, you use x equals 0. But look at this. If x equals 0, what's left? Just the c value. So standard form hands us our y-intercept without working for it. It's this number that's written at the end. Mr. M, what's the big deal? Why don't you want to put that in the box? Because the number at the end of vertex form is something different. So I don't want to say the number at the end. What I want to say is, if you want to know the y-intercept, you plug in x equals 0, and that's true for this as well. It's not going to give you k if you plug in x equals 0. This one, however, will hand you c if you use x equals 0. So in the notes, I'm just going to go ahead and say, oh, I know what my y-intercept is, and I'm going to plot it. But I don't want to put it in this box because I don't want anybody to try to strictly memorize rules. I want you to understand why things work. And regardless of what the equation type is, x equals 0 gives you y-intercept, if your graph has one. All right? You might be wondering what standard form is good for. It's very good for modeling the real world word problems. It's good for that. Models the real world. And anybody that's in physics or has taken physics, you've seen standard form of quadratics used a lot. So how do we graph them? Well, first and foremost, I know the x-intercept, it's free. Y-intercept, it's free. I'll just say, okay, my y-intercept is at 0, comma, and if I plug in x equals 0, I get 0, 0, minus 6. So I have a y-intercept at y equals negative 6. There it is. So I didn't have to work for that. I am going to have to work for the rest of this graph, though. What's a good color to graph in? I'll graph in blue. Using my purple pen, though, I need to find the axis of symmetry. After the y-intercept, it's the very first thing that we're going to find. So my axis of symmetry will be found by using the equation x equals, or the formula x equals negative b over 2a. Every time you replace a letter with a number you're substituting, please use parentheses, please. Lucky for us, because we saw that fraction, it instantly started getting scared, right? Lucky for us, 2 times 1/2 is 1. So my axis of symmetry is x equals negative 2. Ah, I know where there's another coordinate. Yes, what's up? Okay, I know where there's another coordinate. Since this red dot is 2 units to the right of the purple line, there's another red dot 2 units to the left of the purple line. Right there. It is time for me to find my vertex. I know half of it. I know that my vertex will be found at negative 2 comma something, because the vertex is always going to land on the axis of symmetry. They're going to have the same x value. So I just plug in x equals negative 2 to figure out what that y value is. All right, f of, and everywhere I saw an x, I'm going to put a set of parentheses. And I'm going to drop in that negative 2 to those parentheses. Hardest part about this is following the order of operations. Exponents first. Negative 2 times negative 2 is 4. Oops. Well, whatever. I didn't mean to write the plus sign, so I'll just throw that thing in parentheses. Half of 4 is 2. So I have 2 minus 4 minus 6. That's minus 8. The y value of my vertex is negative 8. So on the axis of symmetry, go to y equals negative 8, put you a dot, and there it is. Normally, I would tell you just connect these dots, right? These 3 points are enough for you to know what the shape looks like. And that's absolutely true. However, for funsies, let's say, I want to find another pretty point. My denominator is a 2. So remember what I taught you before, whatever the denominator is, that's how far away from the axis of symmetry you're going to go to find your pretty points. So if we go 2 away, we get there. Go 2 away again, it gets you here to x equals 2. So for fun, to get 5 points, not just 3, I want to plug in x equals positive 2 because it is 2 2's away. Let's see. Exponents first. So that says half of 4. 2 times 2 is 4. And then I have minus 6. Half of 4 is 2. This says 2 plus 4 minus 6. Oh, 0. My graph will have a coordinate at 2, 0. Oh, look, an x-intercept. a solution. And since that is 4 to the right of the purple line, there's one that's 4 to the left of the purple line. And I'm going to connect my dots. Mr. I'm on the homework. Do I have to find 5 points? No. So why did I do it for this one? Because of the next question. That's why. Next question says, take this equation that's in standard form, use its graph, put this in vertex form, and also intercept form, which means I wanted to know where the x-intercepts were. Yes? You mean solve the quadratic? Easier? I don't know. The quadratic formula is pretty hideous. And there's a fraction in this. So, I'm going to be real with you, I hate using the quadratic formula. I try to avoid it at all costs. Also, I designed this one to have pretty x-intercepts. Alrighty. A, vertex form. I'm going to remind you, it is f of x equals, or y equals, whatever, a times x minus h quantity squared plus k. Good news, everyone. We already know h, we already know k, and we already know a. H and k were right here. And a is 1/2. So you take this a of 1/2, this h of -2, this k of -8, and drop them in there, and you're finished. Vertex form, positive 1/2, x minus -2, quantity squared, minus 8, finito. That is vertex form. Vertex form is very easy to get from standard form. You literally just find the vertex and call it a day. So what's the hard part? Do you know x equals -b over 2a is the axis of symmetry? That's the quote-unquote hard part. You have to know it. Now, how would we get it into intercept form if I didn't have the graph, or if I didn't know that the graph was going to go through the x-axis at those pretty values? Well, Jared kind of already hit on it. He said, couldn't we just use the quadratic formula? I would say for now, let's not use quadratic formula. Instead, I would say try to factor. But we don't need to, because we can see the x-intercepts, and we already know a is 1/2. Just reminding you of the equation. Intercept form is f of x, or y equals a x minus p, x minus p times x minus q. We already know a. We know that p is -6, and we know that q is +2. And we drop those numbers in for a, for p, and for q. Earlier, somebody asked me, does it matter which one I call p and which one I call q? The answer is no, that's unimportant. I usually just do p on the left. Do you have to know all 3 of the forms for the graphing test? Yes, absolutely. The a value we know from standard form is 1/2, x minus -6, and x minus 2, finished. So if I hadn't found the x-intercepts here, I would have had to have either solved using the quadratic formula or factoring. Factoring would be the preferred method, and that's what we're going to do at the end of these notes, is factor. Would you like to ask me any questions about that before we move on, though? No? Everybody's good at this and they remember it from Algebra 1? You sure you don't want to ask me any questions? So the general setup is x minus p, x minus q, where p and q are the solutions. P and q are the x-intercepts. So we know that q is +2. So it's x minus +2. No, x-intercepts. Yes. Oh, no. Okay. So the fact that the vertex happens at a 2 and the x-intercept happens at a 2, complete coincidence. Yeah, and that's why I labeled them as H and K, but these were P and Q. Better though? Okay, cool. Can we flip it over? Graph another one? Okay, let's go. What are some things we know? Well, it's got a negative on the front. What's that tell me? Yeah, it points down. And I can easily find the y-intercept. It's free money because if I plug in x equals 0, these two things are gone because they both have x's, and I'm left with the number -2. So I know that my y-intercept is happening at 0, -2, right here. So points down, and we know y-intercept. Okay, let's track down the axis of symmetry. X equals -b over 2a is going to get that for us. So negative, your b value is the 8, and a value is -2. I'm hoping you're seeing the benefit of the parentheses. If I don't use parentheses, it'll say -2 minus 2, which is clearly not the same as -2 times -2. Gives me -8 over +4, which is -2. So x equals -2 is my axis of symmetry. Is +4. Oh no! Why did I put that there? Shucks. Oh no! Look what I've done. Oh my golly. That is awful. Oops. Sorry. That's why we don't do math in pen. Yeah, for some reason I put a negative here. I don't know what happened to my brain. I'm not sure. I'm very tired. Made a stupid mistake. Anyway, if this green dot is 2 to the left of this orange line, there's another green dot 2 to the right of the orange line. We will pretend this orange line doesn't exist. In fact, you know what? Get out of here. This doesn't exist. Get out of here. It doesn't exist. We know that our vertex is going to be at 2, something. We know that. Because the axis of symmetry always goes through the vertex, they're going to have the same x value. We just need to figure out what the y value is. So we're going to throw the 2 into the equation. Everywhere it had an x, I'm going to use a set of parentheses. And that's where 2 will get substituted, like that. Now you just follow the order of operations. Make sure that you do exponents before you do multiplication. This gives me -2 times 4. 8 times 2 is 16, and -2. -8 plus 16 minus 2 is +6. Because -8 and -2 makes -10. 16 and -10 is 6. 2, 6 is going to be where I find my vertex, way up here. If you want a more accurate graph, you can find more coordinates, but you don't need more coordinates for this one. Because I'm not asking you to get this thing into intercept form. That's because it has ugly intercepts. And I can prove it. If I plug in x equals 1, I'll get 2 plus 8. I'll get -2 plus 8 minus 2. That gives me +4. So again, if you plug in x equals 1, you're going to get +4. So clearly, there's not an x-intercept at 1 or an x-intercept at 0. That means the x-intercept is going to fall somewhere between 0 and 1. It's not pretty. Mr. M, do I need 5 points? Nope. You need 3 points. I just got the other 2 to demonstrate that my intercepts are not pretty. We cool with that? Okay. Well, the next example says to get the equation in standard form. There's actually more than one way to do this. We could either use vertex form and get to standard form, since we know the vertex, or we could use intercept form, since we know the intercepts. And it actually doesn't matter which form you choose to use. That rhymes. Just pick one and be good at it. I honestly feel like using intercept form is less work. And that's why I want to do it that way. I feel like intercept form is less work. F of x or y equals a times x minus p times x minus q. I don't know a, but I do know p is -4, so that's x minus -4, which gives me x plus 4. And q is +8, so x minus 8. I need to be able to find a, though. How? How do we find a? I mean, it's not anything new. We've been doing it, Gavin. We could plug in the vertex if we wanted to, yeah. And did it have to be the vertex? No. What else could we have used? Could have used the y-intercept. Or any other pretty point. It doesn't matter. You just use any other pretty point. 100% will not make a difference. He said use the vertex. Okay, fine. Let's use the vertex. 1, -9. Let's plug those two numbers in, because that's an x and a y. 2, not 1. You know, you can say that louder in case I didn't hear you. There we go. So I've got -9 equals, and everywhere I had an x, I'm going to put a 2 in. So we'll put a 2 there, and we'll put a 2 there. That's an a, not a 9. -9 equals a times six times -6 divide both sides by -36 and reduce your fraction. I don't want a decimal, I want a fraction. +1/4. We can write our equation in intercept form now. That's great. That's great. Yeah. But our job was to get it in a standard form. Guess how we're going to do that? How am I going to make it look like this? What do you mean solve it? How? How am I going to simplify? Yeah. So we're going to use distribution. Yep. So we'll distribute the 4 to two things. The x, excuse me, to two things. And we'll distribute the 4 to two things. The 1/4, we'll do that last. So when you go through the full distribution process, you have x times 8, or excuse me, x times x, that's x squared. X times -8, that's -8x. 4 times x, that's +4x. So we've got this -8x and this +4x, and they'll combine, and 4 times -8 is -32. You're finished when you distribute your 1/4. 1/4 x squared minus x minus 8. That is standard form. Would you like to ask me anything about that question, though? No? I was kind of hoping to hear a very specific question, but that's okay. All right. Then the last thing that we need to do is convert an equation without a graph. Eek! Let's do the easy one first. Vertex. Vertex is the easy one. Why is vertex the easy one? Because I can see A. A is -3. But for vertex form, I clearly need to know the vertex. That means I have to find the axis of symmetry first. Negative B over 2A. My B value is -12. My A value is -3. -12 is just 12. My axis of symmetry is at x equals -2. I know half of the vertex. To get the y value, I know an x, plug it in. Right? Not too scary hard. Exponents first. -12, -2, product of 24, and -9. So 12 plus 24, -12. Oh my gosh, I am just struggling. There we go. -2 squared is 4, not -4. Anyway, -3 times +4 gives me -12. -12 and -9 is -21. 24 minus 21 is 3. So I know my vertex is going to be at -2, 3. And I know my A value is -3, so I'm ready for vertex form. Y equals A times x minus h, so x minus -2, quantity squared, plus k. There it is. Vertex form. So you find the vertex and steal A. Hopefully you don't think that's too crazy hard. Unfortunately, we've saved the best for last. If you have standard form and you want intercept form, you're going to need to factor it. We get to steal A. A is -3. But we didn't actually need to steal it because the very first thing you're supposed to do when you factor anything is look for GCFs. And also, if the front number of something you're trying to factor is negative, you always say there is a negative GCF. So our negative GCF is -3. So what we're going to do is we're going to factor the -3 off of our polynomial. And factoring is the inverse of foiling distribution. And since distribution is a multiplication, factoring is the inverse of a multiplication. It's a division. So we're dividing all three of these things by this -3. It's going to give me an x squared plus 4x plus 3. At this point, I would say hopefully you know how to factor. And if you are not a factoring whiz, well, lucky for you, YouTube is full of videos. But the way that we factor is we figure out what two numbers multiply to a times c. Our a is 1, our c is 3. And the two numbers that multiply to 3, we need them to add to our b value, which is 4. So which two numbers multiply to 3 that add to 4? 3 and 1. Somebody said it in the back. 3 and 1. And since there's no number in front of x squared, I can go directly to x plus 3, x plus 1. The negative 3 is on the front. If 3 is one of my solutions, then x plus 3 is one of my no, 3 is not a solution. 3 works out as one of these multiples that have this sum. And since this 1 is positive, I also have x plus 1. There it is. No, the 3 is right here. So this is completely factored. What we actually did was we figured out how to split this 4x. We split it into 3x plus x, and then we factor by grouping. It's a quick shortcut to jump directly to here, but we will review factoring a lot more when we get to solving by factoring, actually. It should be sometime next week. In the meantime, let's say you absolutely just stinking can't factor. Okay, well, you could graph this and then figure out where its x-intercepts are by going distances away from the axis of symmetry and plugging them in. That's really tedious, but if you had to, you could still get an answer correct that way. Yes, ma'am? Where did this 4x come from? So I was dividing all of these by negative 3. See, if you distribute this negative 3, you get negative 3x squared minus 12x minus 9. Which is, so it's right here. I pulled a negative 3 from all three of those things. Any other questions on that? No? Okay. Well, then I guess my nerd emoji comes in. Thanks, folks.